All right, so continuing where we left off, this time with number 13. For number 13, I don't think u sub is going to work because the derivative of x to the 8th is not x cubed, at least not u sub directly. So I'm wondering if we can rewrite this in something that looks more like an arctangent. So I could let this be the antiderivative of x cubed over x to the 4th squared plus 4 squared. Okay, that looks more like something that's going to work because the derivative of x to the 4th is x cubed, and then I have something over, or something squared plus something squared, which looks like a lot like arctangent. So let's let u be x to the 4th. That means that du dx is going to be 4x cubed. So dx will be du divided by 4x cubed. So if I plug things in, I'll get the antiderivative of x cubed over u squared plus 4 squared times du over 4x cubed. Okay, so now my x cubes divide out, and I end up with 1/4 times the antiderivative of 1 over u squared plus 4 squared du. Now there's a couple ways to do this, but I have a little rule memorized for the antiderivative of 1 over a squared plus x squared dx, which is 1 over a times arctangent of x over a plus c. There's another way to do this algebraically, but I'm going to use this just to save a little bit of time. So a in this case is 4. Don't forget I have an extra 1/4 out front. So I'll keep my 1/4 out front and get 1/4. A is also 4, so it'd be times 1/4 arctangent of x over 4 plus c, or 1/16 arctangent of x over 4 plus c. But it's not x, is it? It's u. So I need to change that to a u because that's the variable that I had in my, so it's u over 4 plus c, so that would be 1/16 arctangent of u over 4 plus c. And since u, it was x to the 4th, I would end up with arctangent, 1/16 arctangent of x to the 4th over 4 plus c. Now I'm going to check and make sure that that works, and then I'll erase it. So if I take the derivative of that, keep the 1/16 out front. The derivative of arctangent is 1 over 1 plus whatever's inside squared. So that would be x to the 8th over 16 times the derivative of whatever's inside, and that would be 4x cubed over 4. Well, I can see that these 4's are going to divide out, and I would end up with 1 over 16 times 1 plus x to the 8th over 16. But distributing the 16 through, I get 1 over 16 plus x to the 8th. Oh, I forgot my x cubed. So the numerator would be x cubed here, then x cubed here, which is coming from that x cubed. And that's what I started with. So yes, my answer is correct. Okay, that's good. All right, number 14. This looks like a simple u sub problem because my inner function is x squared, and then I've got a multiple of its derivative outside. So let me just let u equal negative x squared. So then du dx, why is this slowing down again? Would be negative 2x. So dx would be du divided by negative 2x. So I get the antiderivative of x, e to the u, times du over negative 2x. Okay, x's will divide out. And I'll get the antiderivative, -1/2 times the antiderivative of e to the u du. And that gives me -1/2 times e to the u plus c. So that would be -1/2 e to the -x squared plus c. Okay. That seems to be lagging a bit for some reason, but we're getting there. Okay, wow, a lot of problems here. All right, let's see number 15. So we have 1 over x times ln x squared. Well, it really looks like to me like ln x might be our u because we have its derivative, 1 over x. So let's let u be ln x. Then du dx is equal to 1 over x dx. Not 1 over x dx, just 1 over x. Then we can multiply, we can solve for dx and get dx equals du times x. So plugging things in, I get the antiderivative of 1 over x u squared times du times x. X's divide out. Becomes antiderivative of u to the -2 du. Right? 1 over u squared is u to the -2. So that's going to give me u to the -3. Nope. U to the -1 divided by -1. So -u to the -1 plus c. Plug in ln x and I get negative ln x to the -1 plus c. Or -1 over ln x plus c. Okay. This one, since e to the 3x here matches e to the 3x here, I think I can use just simple u substitution. This will be different down here because I have 4x and 2x, so that looks more like an arcsine problem. But if they match, you can probably just use a u substitution where u is going to be your denominator. So if u is 1 plus e to the 3x, then the derivative of u with respect to x is 3 times e to the 3x, using the chain rule. So dx would be du divided by 3e to the 3x. So this antiderivative would become e to the 3x divided by u times du over 3e to the 3x. Okay. 1/3 antiderivative 1 over u du. That just becomes 1/3 ln absolute value of u plus c. And that is 1/3 ln absolute value of 1 plus e to the 3x plus c. Really having trouble keeping up here, but that's all right. 17 looks a little bit different because we have e to the 4x, which is actually e to the 2x squared. So I'm going to rewrite this as the antiderivative of e to the 2x all divided by the square root of 1 minus e to the 2x all squared. Now it looks a lot like an arcsine problem because you want something over the square root of 1 minus something squared often. So I'll let u be e to the 2x. That means du dx is 2e to the 2x, which means that dx is du over 2e to the 2x. So plugging things in, I get e to the 2x times du over 2e to the 2x, and that's over the square root of 1 minus u squared. So again, nice things happen like I want. And I get 1/2 times the antiderivative of 1 over the square root of 1 minus u squared du. Okay, and that is arcsine. So I get 1/2 arcsine u plus c. Plugging in u, I have 1/2 arcsine of e to the 2x plus c. Done. Alrighty. On to 18. 18 looks very similar to something we tried before, where I can't just let the denominator be u because the derivative of sine squared x is 2 sine x cosine x. But I can rewrite this as the antiderivative of cosine x over 5 squared plus sine x all squared. So if I let the u be sine x, then du dx would be cosine x. Not sure why this is taking so long. Thing is really struggling here. And so that means du divided by cosine x would be equal to dx. So plugging things in, I get antiderivative of cosine x. I'm having to really slow down to wait for this thing to catch up. Cosine x over 5 squared plus u squared times du over cosine x. Wow, it's really struggling. So these cosine x will divide out, and I will end up with antiderivative of 1 over 5 squared plus u squared du. And using my rule from above, I know that is 1/5 arctangent u over 5 plus c. So plugging back in u, and then I'm going to have to take a break because this thing is so slow. That is sine x over 5 plus c. Let's see if it's ever going to catch up here. I'm not really sure. There it is, finally. All right, so I'll pause this video and maybe start up if I can figure out how to get this thing to work a little bit more quickly.